Okay, now it should be fine. Yeah, pretty much. So, yeah, as said, my name is Sven Fröhlich. I'm a researcher at the Institute of Quantum Optics at the Leibniz University in Hanover, where I'm part of the group of Milutin Kovachev. And yeah, just to illustrate that maybe shortly, my way. So we're right now here. I'm from up here in Europe. I did my PhD as said at the group at the CSR Clay, mostly working on high harmonic generation in solids, but also on coherent diffraction imaging. And then after my PhD, I was joining Milutin in his group, working now also on imaging, but also as well on laser plasma-based X-ray sources. So a step up in energy from like the up to 100 eV range to like the kilo eV range. Um, and yeah, the main topic today is imaging and kind of the way going there. I mean, you heard probably the Nobel Prize of the last year has gone to attosecond physics, and they are not only like these pulses, this radiation is not only used for attosecond science, but also for imaging and a combination of the two. So I'm starting very basic and then make my way there, showing a little bit what I did during my PhD and what I'm doing now. So to start off, basic imaging. I mean, I guess you've all seen a microscope till now. This has like led to major discoveries in the field of biology, giving us images like this. So bright field microscopy here, but also dark field phase imaging. However, working in the visible light range, this is limited to about 200 nanometers of resolution. As you can see here, nicely shown by the upper limit, we have the wavelength and the NA. To get to this resolution, you have to get to some technical tricks to lower the NA quite far, or get up very high NA, sorry. However, it's worth it as this setup has some really nice advantages. So first and foremost, you can actually image living cells. You can see them moving under the microscope, which is a huge plus. You don't have to kill and prepare your samples in order to image them. And you can penetrate fairly thick samples, as most bacteria, for example, are water-based and therefore have a fairly high transmission for optical wavelength. However, the resolution is limited, and people want to push for high resolutions for a multitude of reasons. First, in biology, you have bacteria and viruses that are significantly smaller than this 200 nanometers and therefore not resolvable with the typical optical microscopes. And you also come up slowly with nanostructures and other fields of engineering that need to characterize these very, very small structures. I mean, if you just think about microchips, somehow you need some quality control for them, and it can't be done with an optical microscope. So people come up with other ways. One of them is electron microscopy, which leaches onto the wavelength, as we will for coherent diffraction imaging do later on as well. And electrons have a fairly low wavelength of like 0.1 nanometer, or not 0.1 nanometer, but this is the resolution you get from them in the end. And there are multiple ways you can use them in a TM or STM setup. However, this comes with disadvantages. Mostly you can still have biological samples, but you have to prepare these samples. You have to bring them in vacuum, which means you can't observe living cells anymore. And the second thing is, second major disadvantage, you have to, the electrons have a fairly high absorption in materials, so you cannot penetrate deep, which means you can only observe the surface of any sample that you want to image. However, as for example the recent pandemic has shown us, we want to have ways of like quickly image very, very small structures. Here the example is a COVID virus. Like these two artistic pictures, and these two are actual electron images of it, which are fairly high resolution, and they are about 60 to 140 nanometers in size, which means you need resolutions below 100 nanometers for sure to be able to image them properly and in a way that you can actually extract information that is important for studying these viruses. A special focus there lies on these spike proteins, as they are the thing that our immune system is latching onto to kill them, and the study and identification of which spike proteins are present on them. So what you saw just now were electron imaging images. Right now, what I'm doing, or what I did a lot, is coherent diffraction imaging. So you don't lower the wavelength by going to electrons, but to going to very high energetic radiation. And with that, you have the advantage that unlike electrons, you can still penetrate in deeper layers of the sample. So you can get depth information out of the sample. And this allows you to do, in the end, what's the goal is these tomographic scans, where you get like 3D images of optimally biological samples, but of any sample that you can essentially penetrate with this radiation. However, the whole thing comes with a catch. Right now, the very high flux that you need for these experiments is mostly available in synchrotrons and free electron lasers, so very, very big facilities. The reason is that they are able to produce this radiation at very high photon fluxes, and the mode for a lot of these experiments is basically that you cluster these samples that you have into a small crystal, shoot at them, and you basically, because of the femtosecond duration of the pulse, you get an image or a diffraction image out of it before it bursts apart, and afterwards you just destroyed your sample. So you kind of like feed them in, take a couple of images, and then you work on the data to retrieve an image out of it. However, over the recent years, there has been substantial effort to go towards tabletop sources in that regime, and to come away from these big facilities to ease the access to these imaging techniques. And that's what I'm going to talk about today. So it's called coherent diffraction imaging, but as this is, as I was told, a class essentially, and not all of you are so deep into this topic, I'm going to start with shortly giving the basics of ultra-short laser pulses and high harmonic generation to come into the sources that we use for tabletop experiments with coherent diffraction imaging. And then from here on, I'm kind of latching onto what I did in my PhD a bit on imaging, and then go into what I'm doing now, which is more walking towards incoherent sources and imaging with incoherent sources in the kilo electron volt range then. And then presenting a little of those sources. Yeah, to start off, laser pulses. I guess all of you know, I hope all of you know, a continuous laser. So this shows the time axis and this kind of the intensity. So it shows a constant intensity over a very long time. Laser pulses now basically take this energy and they bunch it up into small portions. And this results in a field that has a very high peak intensity, but only for a short duration in time. However, this high peak intensity is what's giving you access to like a lot more atomic dynamics in the end. So a little bit of math to get you like the important parameters that might occur in this talk. What you see here is a representation of the electric field. So you see here a normal cosine curve with an envelope, which shows the intensity, which is one of the important parameters that you will see in this talk. Otherwise, obviously, we have a center frequency, and we have some temporal phase, which will be important in the beginning later on, but not so much later on. To go a bit more in this, so pulses, two nice things. So for short pulses, from a Fourier transformation, you directly see essentially that for a short pulse, you need a broad spectrum. That's why it's a center frequency and not like the frequency of the laser. For a longer pulse, you will then have a more narrow spectrum until you get to the continuous laser, where you have a very fine needle, as they need, for example, in atomic physics to like hit certain resonances of an atom. But we, due to the short time duration, need very, very broad spectra. However, what that gives us is very short pulses. So right now, like state of the art is basically femtosecond lasers that you get right out of the oscillator. And due to this very, very large compression of the power into a very short time, you get very high peak intensities, around the 10 to the 12, 10 to the 15 watts per square centimeter. This whole thing, as I'm going to talk about the pulse duration a little more often in this talk, it's normally defined just as the width of the intensity envelope of the pulse at half of the maximum. That's the most common definition. There are a couple of others that, for example, go at different levels, but generally this is the one you will find the most. Just keep that in mind when I'm talking about a pulse width. Then, as preparation, these pulses, as you've seen before in the formula, have a phase. This phase essentially only tells you how the different colors of the field are overlapping in time. So here you see a completely compressed pulse. So all the colors have the maximum at the same point in time. However, you can now imagine if I induce a different phase, which is here like this light dotted line. If I shift this, then suddenly I'm shifting these maxima and I get other shapes. Like if this is still a line, as long as this is a line, you essentially just induce a temporal delay into the pulse, you shift it in time. However, if you have a curvature in this phase, then suddenly you start to shift the wavelength apart from each other in a way that is so-called chirping your pulse, which just means that you go from a compressed pulse to a pulse where you have a temporal disparity between the different colors. So red comes first, for example, and then you slowly, gradually go over into the blue. This especially makes the pulse longer, obviously, but it also reduces the peak intensity. And that was used in the 2018 Nobel Prize, actually, for chirp pulse amplification, which enabled a lot of the very high power lasers that we have nowadays. So the concept of this is you get a pulse train out of the oscillator, then you pick certain pulses, for example, with a Pockels cell out of that. So you are left with only a few, like typical for a Titan Sapphire system, for example, would be 1 to 10 kilohertz, just to give you some numbers. Then you stretch them in time, as I described just now. So you lower the intensity, and because you lower the intensity, you can amplify them much, much more than you would be able to do when you leave them compressed, simply because the limiting factor is this damage on the amplifying laser crystal. And you get a very high intensity. And the nice thing now is that the optics to revert this process of stretching the pulse in time actually are much more resistant to higher intensities than than the laser crystals are. So you can compress these pulses back together, reaching intensities in the 10 to 15, 16, 17 range with this concept. As I said, it was the Nobel Prize in 2018 for Gerard Mourou and Donna Strickland, which opened up then the field of strong field physics quite a lot. And let's demonstrate quite here. So some of you might already know, like second harmonic generation, these perturbative processes in the lower intensity range that are driven, that are based on still bound electrons of the atom. For example, here, second harmonic generation, the classical example, if you see a pulsed green laser, it's probably a frequency doubled ytterbium YAG laser. So you go from 1 micrometer to 500 nanometers, roughly. However, now with the CPA systems, we can go into much higher intensities, where we're suddenly working with free electrons. So there we get plasma generation and especially high harmonic generation, which is the basis for attosecond physics till now, and one of the topics of this talk. And that's exactly the next point. So here you see the two papers that early described high harmonic generation. So the base setup for it is you take one of your really short pulses, typically around 30 to 50 femtoseconds, focus it tightly into a gas jet. Here, typically noble gases, argon, xenon. Xenon was the first one actually, but then they extended to other noble gases. And then you have a simple spectrometer setup. So you have an XUV grating and then CCD to detect your photons. The whole thing is in vacuum, so we are suddenly ranging here in wavelength ranges that are not propagating in air anymore. So this, you have to imagine this whole thing going in vacuum. And what you then see at the end is these distinct odd harmonic peaks that come out of the process. And that's actually what, not what they looked for at the time, but what they realized later is actually connected to attosecond emissions of radiation, attosecond bursts. Conversion efficiencies here are ranging typically in the 10 to minus 6, so they started a bit lower, and nowadays they can get up to 10 to the minus 4. So it's okay-ish for such a process. Next, the next step was then naturally for the Nobel Prize last year, you have to characterize this radiation. So you have to show that it's actually attosecond pulses. And there have been two groups simultaneously working at it, Ferencvaros and Agostini group, both with different methods that are both still in use today. So on the right here, you see what they call streaking nowadays. So you generate your harmonics, you keep a small portion of the IR, refocus on a second gas jet, and then you get and introduce a delay between the XUV and the IR beam. And by doing that, you get a beating signal that you can then calculate back to attoseconds. So this concept here works for isolated attosecond pulses. So like a single attosecond burst of radiation. However, this right method called Rabbit is based on a similar concept. So you also have a delay between XUV and the harmonics, but you then look at an electron signal where you have two pathways to the same energy state and therefore an interference between different electrons that you can observe on your detector. And with that, you can detect trains of attosecond pulses, so multiple attosecond bursts after each other. This distinction is actually important, as in the generation process, you normally generate multiple of these bursts. And why that is, you can see here. So this is the simple so-called three-step model for the generation of high harmonic generation. You start off by shining your laser onto a single atom for now, and by doing so, the laser field is bending the atomic potential. Important, this is only happening when you have very strong laser fields. For low intensities, this is not the case. There you get to like multi-photon absorption or direct ionization if your photon energy is enough. This really requires the strong electric field. And what happens then is you free an electron because it tunnels through this leftover barrier here. And then the electron is free and there's still the laser field. So it's accelerated by the laser field. And as the laser field is oscillating, it has a chance to come back and be accelerated towards the same atom it came from. And while a lot of these electrons are then scattered on the atom or just miss it completely, some of them recombine. And then all this kinetic energy that it was picking up during the propagation in the laser field is converted into a single photon. And this is our high harmonic radiation that we're looking for. Here another picture. So when you imagine these electrons that go out, there are a couple of different trajectories that they can take. And it just so happens that if you look at the field maximum here where they're emitted, so at the highest field strength they are emitted, you have a couple of trajectories that just like miss the atom completely, and you have two coins that come back. They call long and short trajectories, and the important thing here is they are leading to the same energies of the harmonic radiation. So this short trajectory and this long one can lead to the same energy of radiation. The second thing we see here is this happens essentially every half cycle. So every time you have a field maximum, you will get this burst of electrons that are emitted and are then propagating in the electric field. And that means you will get a burst of emission every half cycle. However, maybe some of you thought about it right now already, these energies are not discrete yet. They would not give us these energy peaks that we see in the spectrum. So what gives us these energy peaks is really that we have a continuous energy spectrum, and then we have an interference between these half-cycle bursts of radiation, and that is also the reason why, for example, the rabbit technique was needed for some characterizations, because you have multiple pulses in a normal train. A lot of people then push towards isolated attosecond pulses. You can do that by limiting the radiation to a single half cycle, but I'm not gonna go too much into that as it's not leading really to the topic of this talk. So here you can see then the harmonic radiation that you get out. It's distinctly there's 3 distinct areas of it. Number 1 is the perturbative area, where you see like a steep decline of the harmonics, the plateau, where it's like fairly straight, and then the cutoff region where only a few trajectories are still existing that are coming back, hitting the atom, and therefore the the harmonics start to decline again. Shortly after the discovery, then a basic scaling for this cutoff, so where this cutoff starts, has been theoretically derived and is based on the wavelength, the intensity, wavelength, poneromotive energy, and ionization potential. And this poneromotive energy is then dependent on the intensity as well. So this alpha is usually a factor of like 3.2, 3.17, I think, is the current calculation. And with this, you can roughly scale how high your harmonics will be, especially since people want to push towards like 100, 200 EV sometimes with this cutoff and the highest harmonics that they can observe. Now, maybe I'm from the experimental side of this whole thing, so maybe a few words to like the experimental geometry. How does this look like in the lab? And there are a couple of geometries that you can follow. Here I have shown here 3, which are like fairly popular. One is a gas jet, then in capillaries, and a semi-infinite gas cell. So in a gas jet, you just focus down on a like small jet of gas, which gives you a lot of freedom in the positioning of your focus with respect to the target. Capillaries obviously give you very high intensities over a long range, but make it fairly difficult to handle the gas input. However, as an upside, due to the high intensities, they can produce harmonics from rather low intensity lasers. And then the semi-infinite gas cell as like, let's say, an easy to realize variation of it, where you just have a backing pressure with gas on one side, you have a small metal plate, drill a hole with the laser, and then this small throughput here in this metal plate is serving as your generation point for the high harmonics that are then propagating on the other side in vacuum. Another technical issue, if you want to generate harmonics, as you've seen in the sources just now, before we talked about a single atom we generate harmonics from. In the sources you saw just now, we have extended media. We have, for example, a capillary where we have a long range of gas. And there you have something that you call phase matching, which is common also for lower order nonlinear effects, for example, second harmonic generation, third harmonic generation. And what happens is essentially, if you shine in the laser field, you generate your your harmonic radiation. However, every portion of your the laser is generating it at every point in the medium. However, your second harmonic, for example, has a different propagation speed in the medium than the fundamental laser. So suddenly you have a mismatch between your input laser, the one you're generating with, and the radiation that comes out. And if this mismatch becomes too big, you actually reach destructive interference again. So you have to handle the length over which you propagate and several other effects that influence the phase of the two pulses very carefully to reach an effective generation. So just some shown here. You have the neutral, like the dispersion of the gas. You have the Goy phase of the laser. You have the type of atom you use, so the type of noble gas typically that you use. All these can influence your harmonic generation, and in an experiment then you have to kind of like try out a bit, and also like in the design process before sketch a bit out how you have to combine these different terms, so gas pressure and laser power and focusing of the laser, in order to reach an efficient generation of harmonics. With these harmonics then you can do multiple things. So I'm in coherent diffraction imaging, but you can do direct microscopy with them as well. So it's a lot of imaging. However, you can also do all these attosecond based measurements, pump probe experiments essentially, where you send in a pulse, for example, to excite an electronic state in an atom, and then you probe with the attosecond pulse how the state evolves. So you delay the two pulses with respect to each other step by step, and because of the short duration of the attosecond pulse, you then get a very, very precise snapshot of the state of the atom, and can, for example, with that follow the dissociation of molecules, ionization processes in atoms, and such on. However, as I said, I'm going to concentrate on the imaging side. Just as a side note, this does exist. This is a very big and important topic in physics right now that you might hear more of later on in the courses. However, now coming a bit to my PhD time, so the stuff I really know well. I worked on a sub-branch of harmonics, which are not generating harmonics in gases, but in solids. So typically semiconductors, crystalline structures. And this has only been demonstrated in 2011, so for physics fairly recently. And the energies you reach are not that as high as with gases. However, the setup is much, much simpler, because you don't have to handle a gas in vacuum anymore, but a simple crystal that you place. So you have a solid suddenly, which opens up a lot of possibilities. So for example, a couple of examples of that. Number one here, one of the first demonstrations, the crystal symmetries are mirrored in the harmonics. So if your electron goes towards, for example, this in zinc oxides, towards zinc or towards an oxygen atom when it propagates after ionization, actually makes a difference for the harmonics and is mapped out. After seeing that, people obviously started and tried to calculate back to the band structure of these solids by looking at the harmonics. However, after some early papers, as far as I know at least, it's still an ongoing endeavor, because the calculation of these harmonics are very, very computational intensive and need to be very precise to reach good band structure reconstructions. However, people branched out and then tried out fundamental things, for example, so pre-excite electrons in the conduction band, where they then propagate and see if there's an effect, or go to exotic materials. So here, for example, you have nanotubes, like carbon nanotubes, that they generate harmonics in, and you can see an effect depending on the size of the carbon tube. And then what I focus more on, since you have a solid now, you have the chance of actually structuring the solid. You have a surface, so you can put nanostructures on the surface. And with that, you can actually tailor the harmonic radiation to your favor. Here you see a very simple example of a grating-like structure. So you can disperse different wavelengths right ahead and single out different harmonics. You can also put a Fresnel plate structure on the surface and then directly focus your harmonics without any need of further lenses, for example. And this is, at least in my opinion, one of the most compelling things in solid state harmonics, actually, because you have this freedom of tailoring your material and have like a one give it all sample where you have all the optics that you need, all the all the tailoring of the harmonic beam already included into your generation process instead of having it to do afterwards with, in the XUV range, fairly inefficient and complicated mirrors and optical structures. Lastly, maybe the side comment. It has been shown that these pulses actually are also in the attosecond range, however, in the upper attosecond range, so like a couple of hundreds of attoseconds and not like in below 100 attoseconds like the fast or shortest pulses that have been shown so far. The process here is a little different than in gases. So you have one part that is similar to gases, one part that is different to gases. The first part that is similar to gases is called interband harmonics. And there you have an electron from the valence band that is tunneling up to the conduction band. It's getting accelerated along the conduction band and then drops down back to the valence band. It's pretty much like gas harmonics. However, now this propagation in the conduction band is not in free space anymore. It's in a conduction band. So you have a potential that the electron propagates in. And by propagating in a curved potential, you then get the second contribution, which is so-called intraband harmonics that are just due to the propagation in this curved conduction band. You can reach higher order conduction bands, which you can pretty distinctively see in harmonics from solids, as you not only have one plateau, but two plateaus or even more plateaus that you can access, which correspond to like the first, second, and possibly third or higher conduction bands in your solid. So, again, a little from the experimental side. With solids come other difficulties than with gases. Obviously, if you have a solid sample, you generate your harmonics, you propagate through the sample, so you will have some effects in front of the back surface where you generate your harmonics. So the harmonics are generally so high energetic that they are above the band gap of the solid. So they're only emitted from like the last 10, 100 nanometers of the sample, really, because the other ones are reabsorbed into the medium already after generation of them. But it means your laser is propagating here, and by that you get two important nonlinear effects, which are self-focusing and self-phase modulation mainly. So you change your pulse structure before you reach the point where you generate harmonics. And it has turned out that to reach efficient generation, you actually need to take this into account to get the right and the desired pulse structure here at the back of the sample instead of having it like in the front of the sample where you can easily characterize it. But now let's go back to imaging, finally. So I did imaging with these harmonics from solids in my PhD, and specifically coherent diffraction imaging. So what is coherent diffraction imaging? Basically, in classical imaging, you have some lens system to image your sample onto some kind of camera or your eye, giving typically these microscope images. However, if you go to short wavelength, you have the problem that the refractive index of most materials is going towards 1, which means as lenses are based on the refractive index of the material, you don't have lenses anymore, really. People compensate for that a bit with mirrors. However, for these wavelengths, again, mirrors are very hard to produce and normally are grazing incidence. So you have like a very, very flat incoming beam and reflected beam and are extremely expensive. So they started to think about, hey, what can we do to get rid of this stack of imaging lenses here? And the idea there was, we just shine our laser or our light on the object, and we collect the diffraction pattern that comes out after the object. The problem here is then we measure the diffraction pattern with a CCD, so we measure an intensity. However, the phase is lost in the measurement. And with this lost phase, we lose all information about the object. Then in the 50s, I believe, however, there came algorithms up that actually could reconstruct this phase information based on a couple of assumptions just. And namely, these assumptions are the measured amplitude that you get here, the diffraction pattern, and a so-called object constraint, which is normally that your object has a finite size. So you just assume your object has an end. It's like maybe a circle. It's like a single bacterium, but like it ends somewhere. And just by these two constraints, you get actually iterative algorithms that can work back from just this intensity to the full image. And the advantage of this is now, obviously, we just shine a laser pulse onto a sample and at some distance put a CCD. And that's it. We have no optics here in between, which is elevating all this need for like expensive and rather low efficiency optical refocusing to build these imaging systems that you have in a normal microscope. And this was pretty welcomed, especially by the synchrotron community, where they have a very high flux, but very, very short wavelengths, so high energies in the radiation. And suddenly they could have like rather pretty good images and could use this low wavelength that they have to get high resolution images just from shining their beam onto a sample. Now, there are a couple different types of this. The two important ones for us here are plane wave. So you just shine a plane wave onto your sample. And you see later, tachography. So what you do there is you have an extended sample that is bigger than your beam, and you kind of just step over it, collecting diffraction patterns from each position that you hit. And then by combining all those diffraction patterns and having a joint reconstruction of them, you can get, again, back the image. However, you have more freedom. You have redundant information, which makes the reconstruction more stable and allows you to, for example, also reconstruct parameters of the incoming beam and other side parameters that you might want to know about the sample. So here again, simpler. For me now, during my PhD, the idea was to go from like to generate harmonics in a solid, but instead of like refocusing them on a second sample, so use the solid as a source for the radiation and then work with the radiation, to take the sample itself and generate harmonics inside the sample itself and use those for the imaging of the sample. This is especially nice for nanostructures, for example, like nanostructures that you write in silicon. And this is exactly what we did. So you see here, like we have these small structures that we write into silicon and then generate harmonics in the silicon. We use tachography. So you can see here, we stepped like in a lot of points over the sample in the end, get a lot of diffraction images, and then reconstruct our image based on that, which gives us the advantage that we can have small focus spots as we need them for high harmonic generation to reach the intensities that we need. And we have a very stable reconstruction algorithm, which is always good to have. And yeah, here you see two images of the samples we used just to show you how it looks in the lab. It's a very small laser, here at 2 micron essentially, and just a couple of nanojoules coming in, widening the beam with a telescope, and then focusing down on the sample, which is located here. And then here you see now a spectrometer, which was for discerning the different harmonics. But then later on, we used a camera in this spot together with a microscope objective to get the diffraction pattern on the camera, and took these like about 1,000 diffraction patterns of the sample that we need for the reconstruction. And the reconstructions then look like this. So this is an electron microscope image of the sample. So you can see the structure is just a test sample. It has no real, like the structures here have no real sense. It's just to like test the capabilities of the technique. So we want to have a couple of round structures, a couple of like square structures, a circle here, to have different directions in. And here what you see are two maps. On the middle is the intensity that we reconstruct, and on the right is the phase. You can see here for us now, we get a lot better of an intensity signal. So the sample probably modulates the radiation by transmission. So some in these parts, less is absorbed than here, or more harmonics are generated in these parts and less are here generated here. While the phase information, so the depth of the sample, is rather unclear, which is fine since it was only about 50 nanometers depth of these channels you see here in a darker color. We did this not only with this sample, but we had the luck, I would say, to have older samples lying around that they used already for some experiments with this to generate structured light based on structures you write into the harmonic generating substrate. So here they want to generate some beams with like some what's called orbital angular momentum, but it's not important for now. Important is that you get some kind of like donut-shaped beam out of it. And now what we want to know to verify if our imaging technique is good is basically we look at the diffraction patterns from this, we reconstruct them, and then by numerically propagating the beam forward, we should get to the same structures that they observed in the actual experiment, because the structure is still the same. And this is exactly what you see here. So we could reconstruct these pretty well, which means that our reconstructions are actually usable for real purposes. For example, to monitor these structures online while using them to do some experiments. So now I'm shifting towards what I'm in right now. So we had harmonics as a source so far. Now we go to laser plasmas, which have a slight different approach, as it's not coherent but incoherent radiation. And normally diffractive imaging, as it is diffractive imaging, needs coherent radiation to get a diffraction out of the sample. However, in recent years, there has been some effort to push towards diffractive imaging also with incoherent light, then based on the small fluorescence time of samples that you have, especially right now copper. So this has the huge advantage then that as you can use, for example, copper, if you just stick to copper for a moment, you would be at 8 kilo electron volt with irradiation based on the K alpha line of copper, which puts you far above in energy into a range where most materials are transmitting radiation, giving you a much more flexibility in imaging and opening up new fields of samples that you can image with these techniques. And for that, this is like the next two theory slides. The basic of the technique is correlation based. So what you do essentially is you have fluorescence from the material and you collect your photons at two different points. And by then calculating the convolution of this signal that you get, you can get back some diffractive, some portion of the information that you have in a diffraction image. You then, like if I say two sensors here, two sensors are essentially a CCD array. You have a lot of single pixels, which means a lot of sensors. But yeah, that's how it's based on. Don't want to bug you too much with it. However, it has been demonstrated just recently, like beginning of last year, at the synchrotron, at the FAL in Hamburg, where they took the FAL, focused it on two spots on a copper plate, observed the fluorescence from these two spots, and then based on that could calculate back to this like imaginary double pinhole that these two spots are building. So here you see the actual reconstruction. Here you see their like signal after adding up all the images they took. So it took about 50 or 60 million images, single shot images, to get to this. And like as you can see here, a single image looks pretty much empty if you just look at it. It's really the statistics that give you the signal that you're looking for in the end. And right now in Hanover, one of our plans is to try and go from the synchrotron sources to tabletop sources, which are laser plasma sources. What you do there is you take a laser, an intense laser, you shoot at a metal, for example, and by doing that, you generate a plasma. And inside this plasma, you have very, very hot and therefore fast electrons. If these electrons recollide with the metal, you then create very high energetic radiation that is based on the on two things. First is the characteristic line emission, which is based on the copper K alpha line in that case. So it's like an inner shell transition of copper. And the other one is Bremsstrahlung, which is just based on the electrons being disturbed by the atomic potential, therefore make a curve, and an electron that makes a curve in a field changes velocity and therefore emits radiation, which happens to be then in the 5 to 10 kilo eV range. However, as it is a plasma, it's a pretty chaotic process, so our radiation is not coherent anymore. There's no coherent buildup of the radiation. It's just like randomly emitted radiation. That's why we need the imaging, the new approach for imaging before. And here you see a couple of spectra. So you see here, this bulk is what the Bremsstrahlung is, and these small peaks here, these are the characteristic lines, as you can see here, for like different elements, so copper, nickel, zinc. Each element will give you different lines. It's actually also a technique to identify different elements inside a probe. So for us now, we build right now 3 types of setups that generate this. As you generate the plasma, you ablate material from your target, which means you need to refresh the material periodically, namely for each shot of your laser pulse. And there are different methods to do that. Common ones are here, just a rotating cylinder, or like a small copper tape that you roll through, or even more minimalistic than a wire that you roll through. For some results, so here for the cylinder, for example, you can see that it has some characteristic mission directions, namely mostly dominated geometrically. So you emit most of it in this 45-degree angle because the plasma is generated in this direction and blocks your emission. Otherwise, the emission would normally be in 4 pi, so in all directions. So all these blockages you see here are just like purely geometrical. And what you importantly see is you have a scaling depending on the laser you have. So here you see some femtosecond lasers that you generate plasmas with. And here you see, for example, if you take a high rep rate laser with medium pulse energy, you scale very sharply just based on the repetition rate of the laser. While for femtosecond lasers, it's really each single shot that is producing a lot of radiation. And this is also what you want to have for imaging. You want to have basically enough radiation in a single shot to have a proper imaging, because it allows you a couple of technical applications. For example, if you just think about quality control, X-ray source for quality control, maybe making images of batteries or so. There you would want to have like very fast throughput of a battery, so 1 shot per battery would be an optimal case for that. Yeah, this is for that. Then the tape here, you can see here a schematic. So you come in with a laser, and then the radiation is created by the electrons that are thrown back into the tape and then are radiated through the tape. So the main direction is actually through the tape. Here's our setup, fairly minimalistic. So you come in with a laser, generate on this tape that you roll through, and you then detect your X-rays afterwards, after a window here, as they can propagate in air again. Okay, the video doesn't work. Normally, this is inside the chamber. You see like a really strong plasma ejection of material coming roughly in this direction here. And here, just to show you some statistics about it. So it's fairly stable. However, you have a couple of parameters you have to take care of. For example, the input laser power is an important parameter, as the electrons are at some point just too fast to properly hit atoms inside this copper foil. So depending on the thickness of the copper foil, you get a maximum here for your radiation. And nice for imaging as well, you get a lot of it in one single energy line here in the characteristic copper K alpha line, which for imaging is what you want to have. You want to have a single frequency essentially, because multiple frequencies, especially for diffractive imaging, would smear out your diffraction signal as different frequencies diffract to different angles, and therefore then smear out the image, making it harder to recover. And yeah, that's already it. Just to recap shortly, so we started off with lasers and high harmonic generation. There, the takeaway is probably, okay, we can use femtosecond pulses to generate attosecond pulses inside a gas and have a decent conversion efficiency to use it for further experiments. Coherent diffraction imaging, then that it's actually possible as well to get rid of these imaging optics that a normal microscope has and push towards just observing the diffraction of an object. Incoherent diffraction imaging, same goes for the fluorescence signal. And then plasma ray sources, okay, they can be a future source for enough X-rays to actually come to imaging purposes like incoherent diffraction imaging, but also for plain transmission imaging, as you see it, for example, at a doctor, if you make an X-ray of your arm. And with that, thanks for the attention, and I'm open for questions.